these amazing trusses. And the cool thing is you know how to find the internal force members using method of sections and method of joints. And today we want to talk about a special type of truss member. So our learning objectives for this pre-lesson video are to define and identify zero force members in a truss. Now, before we get going, make sure that you actually have the corresponding lesson handout that goes with this video. It's in our learning management software directly below where you found the video. The handout not only will be useful for taking notes, but it has key directions on things you need to bring to class and complete before class starts. So pause the video if you need to grab the handout. But we now need to get started. So we want to look at this truss, and we're going to apply a horizontal force at C. Now, I have to tell you, I was a little nervous that this truss might be too simple and it might not have really good integrity. And so I went into the library and I was searching in the archives for some more information about this truss. And I ran across this old video where they actually loaded and showed this truss being loaded. Let's take a look. Oh my gosh, that was such a nail biter. I'm so glad the truss didn't collapse. But the video suggested that we could actually use statics to understand why. So let's go back to our truss, but of course now we're dealing with force Shido acting on the truss, and we want to look at the forces at joint D. So of course we know we can use method of joints, and we can put a joint window around joint D. But before we do any calculations, take a moment and see if you can actually estimate what the internal forces are in CD and DB without doing the calculations. But of course, we still do want to do our calculations. So we're going to look at this joint, and we actually want to isolate it and then go ahead and draw the section of the joint. And on our section, we'll have our two internal forces, so force CD and force DB. And of course, we draw those in tension as unknown forces. Now we need to include our coordinate axes, x, y, and then we can start doing our static. So let some forces in the x equal to 0 with to the right as positive. So we'll have 0 is equal to negative force CD, or force CD is just equal to 0. Well, then we can sum forces in the y equal to 0. Vertical can be our positive, vertical up, and would have 0 equal to negative force dB, or force dB also equal to 0. Now, did that match what your estimates were? Remember, not just the truss has to be in equilibrium, but so does every section or cut that we make. And so if there are no external forces at that cut, then the internal forces must be 0. But what would happen if we actually looked at our truss again and added force Shido now at D? Well, fortunately, the movie did just that, so we can watch. But I tell you what, I don't think they had stunt doubles back in the day, so I sure hope Shido got some hazardous pay. Let's see. Statics really is our hero. It's our friend for life. And supposedly it can tell us why, again, it didn't collapse. So we'll look at joint D and we'll isolate it again and again try to estimate what's happening in members CD and DB. But again, we'll go ahead and do the statics, so we'll need to draw our joint. But this time, we also have force Shido acting to the right, but we still have our force DB and force CD acting in tension. Now, we'll use the same coordinate system, so we can sum our forces in the x equal to 0. To the right would still be positive. And in this case, we'd have 0 equal to force Shido minus our force CD, or force CD is actually equal to force Shido, so it's no longer 0. But then when we sum forces in the y equal to 0, again calling up positive, it's going to look like our old calculation, so 0 equal to negative force dB, or force dB equal to 0. And so we did these 4 status calculations, and for 3 of them we found internal member forces equal to 0. And maybe that shouldn't be a big surprise, since 0 force members was our learning objective, and these are special types of members with 0 internal forces. And you might be asking, why? Why would we have these extra members that don't carry any load on a truss? It doesn't seem sustainable. It kind of doesn't make sense. Well, there's actually a variety of very good reasons to have these members in a truss, and we're going to go over those in detail when we get together in person in class. But for now, I want to provide you with a couple of rules that you can use to quickly identify these 0 force members. And so our rule number 1 for 0 force members, which you can already see on your handout, that rule number 1 is going to occur when 2 members are at a joint. Now specifically, we mean 2 non-collinear members form a joint and no external force occurs at that joint. Now you have that written there, but we now want to draw what that looks like to make sure you understand what we mean by non-collinear, not in a line. So go ahead and draw this joint. And so I'm going to go ahead and draw them 2 members basically at about 90 degrees apart. They don't have to be 90 degrees, they just can't be 180. And to make our lives easier, I'll go ahead and align the XY coordinate system with my 2 90 degrees apart non-collinear members. And so if you think about summing forces in the x equal to 0 or summing forces in the y equal to 0, it should lead you to something similar to what we saw in our first truss, that both of these members are 0 force members, or ZFMs. So both members are ZFMs. Make sure you get that in your notes. In fact, it's so important, let's give it a red cloud. Now we do have a second rule. You can see it there on your handout. ZFM rule number 2 occurs when 3 members form a joint. But in this case, it's 2 collinear and 1 non-collinear member forming the joint. And again, no external force occurs at the joint. So again, I want you to draw what that looks like. So we'll draw a sample drawing. And in this case, I'm going to go ahead and make the 2 collinear, the 2 in a line members, we'll make those horizontal. So we have these 2 collinear and 1 non-collinear. And the non-collinear doesn't have to be at 90 degrees. It can be at any angle as long as it's not in the same line. And I've gone ahead and aligned the x-axis with the collinear members and the y as just a vertical. And so you can see if we were to sum forces in the x direction, all 3 members have an x component, so that doesn't really give us any useful information. But if we sum forces in the y direction, only the non-linear member has a y component. So there's only 1 member in our equation, and so what that leads us to is that the non-collinear member must be a 0 force member. So when you have these 2 collinear and 1 non-collinear, the non-collinear member is a 0 force member. Again, red cloud. And so we're offering you two sets of rules, or two rules, to help guide you in finding zero force members without having to do calculations. And so basically we have defined a zero force member and we've given you the tools to identify, but still need to practice. And so when you come to class, be prepared to apply these rules so you can practice, so you can feel confident that you can identify zero force members in a truss. Thanks for watching.